Still in topic number 1, we're going to go ahead and talk about inverses and inverse functions. We're going to determine if a function has an inverse, and we're going to be able to graph that inverse simply as a reflection over the line y is equal to x. So, the inverse of a function is where the domain and the range values are switched, or another way to say it is the x and y values are interchanged. So if originally I had x comma y, the inverse then is going to be y comma x. Graphically, what this means is that the inverse in the original function are reflections over the line y is equal to x. And if you think about it, that's kind of what's happening here. If I put a mirror right in between there, we have xy looking into the mirror, comes back out as yx. They are mirror images of each other, reflections of each other over the line y is equal to x. So, very simply, if I gave you the original function here, or in relation in this table, what would the inverse look like? Well, 17.5 would turn into 5.17, 0, -4 would turn into -4, 0, and 12.3 would turn into 3.12. Same thing with the mapping diagram. If my original mapping diagram looks like this, the inverse, we would simply swap the bubbles. 8, -20, and 9 would be on the left, and 19, 2, and 5 would be on the right, and then I would simply just match up the arrows like I had before. 19 still goes to, -20 goes to 19, 8 goes to 2, and 9 goes to 5. Not so bad. But we're not going to spend a lot of time on tables and mapping diagrams. We really want to jump into looking at it when we have a full graph or just ordered pairs, and how the original and the inverse look here. This is what we're going to encounter out throughout the rest of the year and in the higher level math classes. So starting off, I've graphed the original function for you. Let's go ahead and find 3 coordinate pairs and name them. I picked -5, 3, -3, -1, and -2, 0. Well, if that's the points x and y from the original function, the inverse points are just simply going to be x and y values switched. 3, -5, -1, -3, 0, and -2. And if I plot those points, you'll notice that they are all reflections across the line y is equal to x. Well, I can go ahead and connect these dots and make the graph look similar. And we can see that this whole graph is in fact a reflection of the whole graph. The question is then, the question we're going to ask is the inverse a function? Well, since we graphed the inverse function, does it pass the vertical line test? Well, in this case, no, it does not. We can draw a line and it intersects at 2 points, so this is going to be no, fails the vertical line test. Well, let's take a look at the second example. Another graph. Let's pick 3 coordinates and then write the inverse coordinate point. So my 3 points from the original graph, I simply switch the x and y values to get my inverse coordinate points. And plotting them, we can see that, hey, it looks like they are in fact mirror images across the line y is equal to x. Connecting the dots to make the full graph, we have our full inverse graph. And the question is it a function? Well, in this case, before it was no. In this case, it is yes. If we were to draw vertical lines through it, it passes the vertical line test, which meaning that every x value has exactly one y value. Let's take a look across the way. Why don't you go ahead and try the 2 examples that are there. The answers will appear in 3, 2, 1. In our first example, we see it fails the vertical line test, and part practice B, it passes the vertical line test, which kind of begs the question, do I actually have to graph the inverse every single time? Is there a shortcut way for us to actually come up with whether or not the inverse is in fact a function? Well, there actually is, and that is from the horizontal line test. So I consider this a shortcut for the vertical line test on the inverse. Basically what that means is if I look at the original graph of the function, I can determine whether or not the inverse, which I haven't graphed yet, is a function by performing the horizontal line test. Meaning that if I draw a horizontal line through the original graph of my function, if it only intersects at 1 point, then that means that the inverse would be a function. If it intersects at more than 1 point, like it does in these 2 examples, it would not be a function. So again, these are looking at the original graphs. So these are the original graphs that are telling us information about the inverse, which we have not graphed yet. It kind of saves us from having to draw in the dotted line and actually go ahead and draw in the inverse like we had done before. We can simply just say, all right, well, on the original graph, does it pass the horizontal line test? If it does, that means the inverse, which I would have drawn, is in function. is in fact a function. If it doesn't, then we are in fact not going to be that way.